We have now a fourth example of a buffer problem. Let's read it. A 1 liter buffer solution is composed of some KHP, 1.36 grams of it. Grams per liter. They want us to calculate a molarity for that, because that's what we're going to need. And 5.677 grams of the disodium hydrogen phosphate. We can also calculate the molarity of that. I'm sure we're going to need that. Also notice that we don't have any phosphoric acid here. We have one where 1 H plus is removed, and the other one where 2 H plus is removed. That makes this our weak acid and this its conjugate base. That's critical to understanding it. So make sure you understand that you take away H plus to form its conjugate base, which is the disodium hydrogen phosphate. They do give you the Ka of the first one, which gives it away, but in some other problems they might ask you to just look stuff up, so they don't tell you that at all. They give you its molecular weight. That's convenient, and this, because we just figured out we're going to need that in order to give out the concentration in moles per liter, so that should help with that. And they want the pH of the buffer solution. I always think Henderson-Hasselbalch when it says what's the pH. And then a method to lower it by 0.5 units. That sounds like a tougher type of problem. Let's take a stab at that after we've solved A. I'll show you a traditional way of solving A, which I don't like as much, but I'll show it. A Henderson-Hasselbalch method of solving A, which is very fast, and then we'll take a look at B. Okay, Henderson-Hasselbalch, you just write down the formula. All we need is the negative log of that number and the concentration of A minus. That's the one that lost 2 of them. That's the concentration of this one, which we're going to have to actually calculate, right? But we can do that. And the concentration of HA, which goes on the bottom, that's the 1.361. And then we plug it all in. And here it is in one quick step. So the negative log of the Ka, fine, and the log of 5.67 grams, whereas it's 141.96 grams per mole. And that should give us the molarity of that, since it's a 1 liter solution. And similarly for the HA, the KHP, the same thing. You can't abbreviate it more than this, and this might be a little bit too rapid for some people, but you plug that all in one fast step, you got a pH of 7.81 for this buffer system. The traditional way is to first write down the chemical reaction. And here it is shown in a little bit more detail to get the same number, 7.81. That's in case you wanted to break that into pieces. Okay, traditionally it might help to write down the chemical reaction, right? We've got the phosphate monoanion turning into the phosphate dianion plus H+. That's the KHP. This is the disodium hydrogen phosphate for there. There's the Ka, and here's where really the logic of the overall problem comes in. They give you you want to just hope they gave you everything except one thing here. And they did, right? We want the pH. They should be giving you everything except H+. We have to calculate this one, we have to calculate this one, but they gave you enough information to calculate it. Let's do them one at a time. Let's find the KHP concentration. Well, it's 1.36 grams per liter, and that many grams per mole. We end up with moles per liter, which is concentration, and it's very short, almost exactly a 0.01 molar solution. For the disodium hydrogen phosphate, exactly the same calculation tells you we're very close to a 0.04 molar solution. Good, now we got enough to solve for H+. See how we have everything except H+. When we solve for it, we find that it is about 10 to the minus 8th, so the pH should be somewhere close to 8, and it is. The pH is 7.8, and this compares both methods, so do either one. I greatly prefer this one, but I'm biased. Finally, we need to figure out a way to lower the pH of the pH by 0.5 units. Well, it's 7.81. I guess we need to go to 7.31. And if we have a pH 10 to the negative pH tells us H+, which will be right there, that part. We also know that this concentration has not changed. All we need to do is find the new concentration of the where is it, of the monoanion, the KHP. So we're going to find out the concentration we need. We're going to convert that to grams. And there's one last thing you need to remember before you come up with the final answer, which is there's already some KHP. This will tell you what the new total concentration is. Subtract the new grams from the old grams, and it should tell you how much you need to add. Did that make sense? Let's see. Okay. So first we recognize that the pH is going down by half a unit from 7.81, so it must be 7.31. The H plus, which we're going to need right there, will be around 10 to the minus 8th, so we solve for that. It's not the same number as here because the pH is different. So there it is. That has not changed. That has changed. Mathematically, you should be in a comfort zone. You can solve for x by cross multiplying. And x is 0.03159 molar of that solution, and there's its molecular weight. So let's go from moles per liter to grams per liter, and since it's a 1 liter solution, thank you for making it simple there, that'll be the same number of grams. So from moles per liter, there it is, to grams per liter, so we need to have a solution that has 4.29 grams in it. Well, we know that it had 1.36 grams in it, so we need to add 2.94 grams of potassium hydrogen phosphate to that solution. I think this is the most challenging form, perhaps, of the buffer solution problems that you might see on an AP exam. This is our fourth example of a buffer problem.